Welcome to session 16 in our series on electricity and magnetism. In our last session, we explored something called electrical resistance. That's something that all everyday wires have. And we took a look at what happens when we have an extension cord. In particular, we use this. We have an extension cord that has plenty of capacity for the amount of amps we're going to flow through it. In other words, it's not going to overheat. But if we make it long enough, we run into problems. We have something called voltage drop. That is, some of the voltage that we start with is being lost in pushing the electrons through the wire to where we want the power. And that results in two kinds of problems. One is the voltage at the end of the wire is not adequate to make our equipment work properly. In some cases, if we try to make it do the piece of equipment work right, like a power saw or a compressor, it may actually damage it with the lower voltage. The other problem is it wastes a lot of power. So all that voltage that's being used to push the electrons is being wasted. Now, we're only talking about moving electricity a few hundred feet with extension cords. But the people who bring you power, your utility company, has to deal with moving electricity miles, tens of miles, hundreds of miles, maybe even more. Let's take a look at what they deal with in order to do that efficiently. I've got a little sketch here on this whiteboard. These are all our different sources of energy that we can convert into electricity so we can send it where we need it. So there's a conventional natural gas, coal, nuclear, and then there's renewables, geothermal, hydro, wind, and solar. Now, regardless of which one of these we're using, we often want to be able to move that electricity somewhere else. In some cases, it's being generated far from where we need it. The dams and the hydroelectric plants have to be close to where there's a river. We would like to put the wind farms where it's nice and windy. The power of the wind goes as the velocity cubed. That's V times V times V, not just V. So if I double the wind speed, I get 8 times the power for the same wind turbine. That's why we want to put them in a windier area. Now, most of the power we get right now is through a generator. All these different sources, except for solar, photovoltaic, and you might say fuel cells. All the rest of these, the power comes through rotating a generator. You have the hydraulic turbine for hydroelectric power. Wind turbines are obvious. And then there are steam and gas turbines for these thermal plants. So we're running the generator. The generator typically produces power at something on the order of 2,000 to 8,000 volts. The K stands for 1,000. Now that sounds like a real high voltage. Well, it is for us because we're used to working with 120 and 240 in our homes and some of our businesses. But for sending electricity long distances, 10, 100, 1,000 miles, that's not nearly enough. We often will raise it to 100,000 volts to 500,000 volts. How do we do that? Well, we use something called a transformer. The transformer transforms the electricity. It doesn't create new energy. Remember, voltage isn't power. Volts times amps equals power. And a transformer will raise the voltage and lower the amperage, and then we will send the power using the higher voltage. Now let's take a look at a picture of one of these. Here's a typical array of high voltage transformers. It looks something like that. And then that would send power, after that's left the power plant, we would send power down the power lines, and then it would get close to, let's say, a city, an urban area, metropolitan area, and now we've dropped the voltage, and that process kind of continues. I've skipped a couple of steps here. We would reduce it until we're at voltages that are safe for people to be close to. Let's take a look at a couple more transformers. So here's perhaps another substation, lower level voltage, and here's probably something you're really familiar with, the pad mounted transformer. The power comes in underground, leaves underground at a lower voltage. And here's one at a big box store. And you'll notice the numbers here. It says 1000 kVA. Now kVA is closely related to kW. The K is 1000, the V and the A are volts and amps, volts times amps, which is typically watts, except with alternating current, it's not exactly the same. Alternating current is kind of complicated. Now, for all the stuff we're going to be doing today, you can treat volts times amps as the same as watts. We're not going to be doing anything tricky, so it will still be volts times amps will still represent watts. Let's look at a couple more typical transformers you're familiar with. These on a pole here, they're serving these buildings with a drop down to the various commercial buildings. Here's the high voltage lines up here. Notice they're thin, even though supplying all these thick wires. We'll learn about that in a little bit. Now, here's residential. Let's get this bigger here. Let's zoom in and take a look at what's going on here. So here's a drop, okay? There's a drop to a house across the street. And then it looks like there are two services going down two conduits into the ground and over to the houses on this side of the street. So that transformer can deliver power either overhead or through a underground service to the homes. So why do we raise the voltage and lower the amperage? When we raise the voltage, we don't have to move as many electrons down the wire. And with less amperage going, we have less losses in the voltage. If I increase the voltage by a factor of 10 and reduce the amperage by a factor of 10, that gives me a 100-to-1 advantage. Theoretically, it depends on how good my transformers are. If my transformers are perfect, I have a 100-to-1 advantage. What that means is I can either, given a certain situation, certain size wire, if I increase the voltage by a factor of 10 and reduce the amperage by a factor of 10, I can go either 100 times farther than with the lower voltage, or I can use wire that's 1/100th as large in cross-section, or some combination. I could go 10 times farther with wire that's 1/10 as thick. So we're going to kind of explore that with some experiments. We're going to duplicate what's going on here from the generator to the first transformer and to the second transformer. Okay? This is our generator. And normally if I were in the classroom, I'd have a student turn the crank, a strong student. Takes some effort to keep this going. But there's no students here in my shop. So we're going to use an electric motor to drive this wheel, which will drive the alternator. And I'll show you the motor real quick. There it is down there on that little pulley. Okay, so that's our power supply. That's our power plant think of the crank, or the motor if you wish, as being our wind turbine, a hydraulic turbine, our steam turbine, whatever you want. So that's our source of power. Now, what we're going to power in these experiments is a light bulb. Roughly I'd guess it's a 12-volt bulb. It's a headlight. These two are identical. Millions have been manufactured, so it's not like I'm using, when I switch back and forth, I'm really not switching the load. It's like the same load, okay? It's just I might use this occasionally for convenience. So I'm going to plug this in here. Wait a sec here. I forgot to put up our chart. I have done this several times. So to save time, the numbers are already up there, but we're going to do the experiment, and you will see that I'll point to the numbers that we would have measured anyway. So here's our light bulb right at the power plant. And what do we got there? 9.5 volts, 4.5 volts, which zero distance away from the power plant, 9.4, 4.4, pretty much the same as what's there, about 41 watts, okay? We might be producing slightly more right now, more or less, okay. But where we need the power is almost never at the power plant. So this is going to be our transmission line, our first one, 500 feet long. This wire will carry out in the open probably 20 amps without any trouble at all in terms of overheating. It would never overheat with 20 amps out in the open. We only want to flow about 4.5 to get the same amount of light. 500 feet long. It's a number 14 wire. Now we're going to use this bulb because I have meters connected to it, and we can measure what's getting to the bulb. Not too bright. What are we getting? 3.3 volts, 2.6 amps. That's this one here, 500 feet of number 14 wire, 3.2 volts, 2.6 amps, which turns out to be 8.3 watts. This times that equals that, okay? All right, so let's see what we can do by using transformers. So I'm going to unplug this, and we'll plug in the first transformer, the step-up transformer, right here. And to show you that we are increasing the voltage, it'd be hard for you to read these meters. They're kind of tiny. These are 120 volt bulbs. Now I've measured what's going on here before, so that's about 90 volts are lighting these up. So we got about a 10-to-1 increase in voltage. Okay? So let's plug our extension cord, or our transmission line, into here. Now the output of this is still a high voltage. Now if I were to plug one of these lights directly into here, this would not work well. This is high voltage, low amperage. It looks at this like a short circuit. In fact, I'm going to do it briefly. If you'll keep an eye on the ammeter, the bulb, and listen to the sound change and how it slows down, this bulb won't light. That'll go to 16 amps. Watch this. Okay? You hear that? Ooh. All right. So it's a mismatch. What we need to do is now lower the voltage, increase the amperage so we can operate this bulb. So I will plug in this transformer, and then we'll plug in the bulb into its output. And pretty good. Not quite as bright as at the power plant, but pretty good. 7, 7.1, 3.8. Well, I'm doing better than last time. So here's the 500 feet of number 14 with a transformer. I've got 6.9. This is a little higher. And 3.8. So we're getting a little more than 26 today, but about that amount. Pretty good, huh? See what the transformer did for us already? All right, I'm going to put this here for later. It's not doing anything because there's nothing plugged into it. What we're going to do now is, instead of using the number 14 wire, we're going to do the same experiment with 500 feet of number 20 wire, which is thinner. And the ratio is 4 to 1. In other words, this is 4 times more cross-sectional area than with this one. But since you can't really see it closely, I drew 2 circles that are completely bigger than the wires themselves. But that's what a 4 to 1 ratio looks like. Okay, so you can get a feel for it. That's a lot more copper than that. And this is the one we're going to use. So here is our coil of 500 feet, number 20 wire. And let's see if we can reach a little bit tight here. That's 1/4 the thickness, same 500 feet. That's this line right here, 500 feet of number 20 with a transformer. We're getting 6.8, I don't know, today it's a little better than yesterday. 6.8, pretty close to 6.7, and 3.75 here. So we may be getting 26 here, we were getting 27 there. Almost the same amount of energy with 1/4 the wire thickness. Okay? Because there's so few amps moving in the 500 feet. We raised the voltage, lowered the amperage. Now, that was only with 500 feet. I'm going to add another 500, another 500, another 500. Okay? So that's a total of 2,000 feet of the skinny wire. Let's see how much electricity we can get at the end of that using the transformer. This extension cord just brings the power up to the front here. Okay? What do we have? 5.8, 3.4. Very close to the 5.7, 3.4, 19.4, maybe slightly more because today I'm getting a little higher voltage. 2,000 feet. And we're still beating the direct one here, the 500, way beyond that, okay? We're losing a lot of power, but we're putting out some energy here. Now I'm going to ask you to use your imagination, okay? Because I don't want to buy a whole bunch more of those coils of wire. They take up a lot of space, they cost money. So what we're going to do is we're going to simulate additional coils of 500-foot coils, okay? These are called resistors, because that's what we're interested in, what resistance does to the flow of electricity. And these 4 resistors are equivalent to 2,500 feet of number 20 wire up and 2,500 feet back. Okay. So this represents 5 rolls of the number 20 wire. This one here represents 10 of them, 5,000 feet up, 5,000 feet back. So I'm going to insert these in sequence into the circuit. I'm going to add it to the 2,000 and we'll see if we can light that bulb. And this one here. We're 4,500 feet away from our power plant. We've got 4.4 and 3. 4.4 and 3 is 13.2 watts. That's at 4,500 feet with a transformer. Still much more than the direct 500 feet with the heavy wire. Much more. Let's go to the limit now. We're going to take this to here. We're adding 5,000 feet, almost doubling the distance. Now you're probably not terribly impressed with that. We've got 2.6 or 7 and 2.3, which is what I had here. 2.6, 2.3, right around 6 watts with 9,500 feet with a transformer. We are now just a little bit less than the 8.3 direct. Now, like I said, you may not be that impressed with that, but let me show you what we started with. When we first hooked up this big heavy wire, this one here, they're almost the same. This one's a little bit brighter, but not much. They're very close. But we're going, with this one, we're going 9,500 feet, not 500, with 1/4 the cross-sectional area for the wire. Now you remember when I told you about if you went 10 times the voltage and 1/10 the amperage, you'd have a 100-to-1 advantage? Well, we've got 19 times the distance and 1/4 the area. 4 times 19 is 76. We're getting 76 of the 100. Why aren't we getting more? Well, these little transformers that you get are typically nowhere near as efficient as the big ones that the power companies use. So mine are only, the two together working, are probably about 72% efficient, which is about what we're getting here. So let's turn these off. Now, don't get me wrong, I'm not saying that thin wire carries more electricity than thick wire. If we had done all of these last several experiments, all of these with number 14 wire, we would have gotten more power to the bulb. But the point I wanted you to see was that starting with 500 feet of heavy wire, if we want, by using the transformer, we can go farther with thinner wire. Okay? And that's how we're able to send electricity enormous distances without having wires that are that big around. Okay? Now, one other thing I want to say, in case maybe you're a teacher and you want to do this experiment, you do not want to have two separate coils of wire as your conductors. You know, obviously you can't go 500 feet or 1,000 feet in your classroom, so you'll keep things in a coil. You want the two conductors, the up and the back, to be right close to each other, and then you wind the pair, or it might come that way. You get a spool where the two are together. What that does is it minimizes the electromagnetism that would be caused by that. If you have two separate coils, say this red one is for the power coming out and the green is power coming back, these will act like electromagnets. And with alternating current, you have something called inductive reactance, which will interfere with the experiment you're trying to do, because it restricts the flow of electricity. So you don't want these separate. You want them wound together in your coils. Okay, in our next session we're going to explore how a transformer is kind of put together. What are its main parts? How does it change the voltage and amperage? And what kind of electricity do you need to make it work? And then the next session we'll deal with how do you generate that electricity. So thanks for visiting, and I hope to see you next time. Bye-bye.